If you need to, pause the video, read it for yourself. Otherwise, I'm just going to give the quick summary of it. Here we have a bullet that's initially moving at a rate of 284 meters per second to the right. It's going to strike a stationary block. This particular block has a mass of 1.4 kilogram. And then both the block and the bullet will move to the right after the collision. The block will move to the right at a rate of 0.43 meters per second. And then the bullet will move at a slower rate of 234 meters per second. Here's part A and B. Part A asks us to determine the mass of the bullet, so let's crack that out. So in order to determine the mass of the bullet, I'm just going to set up conservation of linear momentum. Initially, the only object that's moving is the bullet, so the only term that's on the left side is P1I, P1 being for the bullet here. The subscript indicates that the mass of the bullet is denoted as M1, so that's what I have here is P1I. On the right side, it says that the block and the bullet are separated, and they will both have different speeds for this particular problem. So I have a P1F and a P2F for that reason. Here, I'm just going to plug in values that are given to me. M1, I don't know what it is. That's the mass of the bullet, which I'm trying to find. The initial velocity of the bullet is 284 meters per second to the right. And then P1F here, once again, M1, I don't know, so I kept it as M1. I do know that, however, the velocity of the bullet is given as 234 meters per second once it passes through the block. And then P2F is broken into M2 V2F, M being 1.4 because that's given. The mass of the block is given. And then the problem states that the velocity of the block is going to be moving eastward at a rate of 0.43 meters per second to the east. So that's a positive value. So therefore, I'm just going to simplify this on my calculator and combine like terms. Here we have 284 M1, and here we have 234 M1. So I want to move this 234 M1 or M1 times 234 to the left side just to combine like terms. So therefore, I want to subtract it because this is a positive term initially on the right side of the equal sign. Moving it to the left will change sign. And then 1.4 times 0.043 will give you about 0.62. And then to simplify this, I'm just going to combine like terms. Excuse me, I'm going to combine like terms by factoring out M1, okay? Because both these terms has an M1, so an M1 in the front and an M1 in the front here. So really I can say on the left side here it's just M1 times 50 because 284 minus 234 will give me a difference of 50, and I already factored out the M, which stays outside the parentheses. So really here I have 50 M1 or M1 times 50, which is equal to 0.602. So to get M1 by itself, I would just divide both sides by 50. So 0.602 divided by 50 will give you about 0.01 kilograms, okay? And therefore the mass of the bullet is about 0.01 kilogram. And that is our answer. And then let's do part B. Part B asks us to calculate the change in kinetic energy of the system during the collision. So in order to find the change in kinetic energy, I just have to do KEF minus KI of the whole entire system. Initially, there's only one mass moving, and that is the mass of the bullet. So you notice here KI cis is only one term. However, KF cis here has two terms because after the collision, the block and the bullet moves off at different rates. So I'm just going to say 1/2 M1 V1F squared plus 1/2 M2 V2F squared. And then we're going to subtract that from the initial KE of the system, which is only contributed by the bullet. So here I'm just going to plug in values. Here's the 1/2, M1 being the mass of the bullet, which I just calculated previously in part A, which is about 0.012. And then the final speed of bullet 1, or the mass 1, which is the bullet, is given as 234. So the 234 is given. And then the second term here, 1/2 M2 V2F squared, M2 being the mass of the block, which is 1.4 kilograms, that's given. And then the final speed of the block is also given as 0.4 in the statement here where I'm circling back at the top right of the screen. And we're going to square that. And now I put everything in bracket here because we're going to add KEF together and then subtract it from KI. However, you notice here KI is only the mass of the bullet and the speed of the bullet because the block was initially at rest. So I'm just going to simplify these terms. Hopefully my calculus work is good here. It's getting late. The first term here, I think, should come out about 328.54. The second term here, 1/2 times 1.4 times 0.43 squared, should be about 0.13. We're going to add those two terms up and then subtract it from the initial KE of the whole entire system, which is about 483.94. So if we simplify that first term, add those two things together, it should be about 328.553. Subtract that from 483.94, and therefore the change in kinetic energy should come out to be about negative 155.387 joules, and that would be that is our answer for part B. Okay. All right. Hopefully my calculator was on point. Stay nerdy. Don't be whack.